Assalamualaikum and a very good morning to everyone. My name is Ramzan Ali Sayani and I'm going to represent the introduction part to our safety video from Group Selangor. Okay, so moments are usually defined with respect to a fixed reference point. They deal with physical quantities measured at some distance from the reference point. For example, moment of force acting on an object, often called torque. So torque is actually the product of the force in the distance to the object from reference point. The moment of a force about a point provides measure of tendency for rotation. The force vector can be defined by two things, which is first its magnitude and second its direction. So its effect on a rigid body also depends on its point of application.
Okay, hello guys. My name is Idris Fahmi and I'll be talking about the application of moment on door. So as you can see in this picture, as the person applies force with magnitude F, the turning effect of the door depends on the magnitude of force and the perpendicular distance between the line of action of the force and the pivot, or in this picture, in this situation, the hinge of the door. Therefore, the moment could be defined as moment equals to force times with perpendicular distance of force from pivot. So, however, sometimes people doesn't like to push the door at 90-degree angle. So, in the situation where the force is applied from from angle other than 90 degree, so the perpendicular distance between the hinge and force is given by D equals to R sine theta. And now our new formula for moment is force times R times sine theta. Oh, that's all. Oh wait, I have something to add. So the concept of moment of force is useful when considering situations in which a body is acted on by a number of forces which are in equilibrium. If the person pushes on the door but the door does not move, when he push the door but it doesn't want to move, so it means that the turning effect to the spring, you see the spring, this spring, that spring must be equal to the magnitude of the force that was applied but in opposite direction due to the in opposite direction of the force that was applied by the person pushing the door. So into the next one.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azran Hidayatullah bin Shaini, and today I'm going to explain to you about free body diagram of a moment of a door. Okay, as it can be seen in this picture, the person is trying to push open the door, but he finds it hard to do so because the angle between him and the door is not 90 degree. It would be easier for him to push the door if he applies the force further away from the hinge and he pushed the door at from 90 degree at the door. Okay, the example is this. Look, the force he applied is further away from the hinge and the degree angle is 90 degree. So that's all. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafiz Muhammad Zakwan. Okay, now we will talk about moment of inertia. So the question is compute the moment of inertia of the door with respect to the x-axis. So the formula is Ix equal to 1/3 bh3. So the B is, the Y is 1 meter and the height is 2 meter. So the IX is 1.667 meter power of 4, and another one is respect to y axis. So IY equal to 1/3 BH3. So we put the H and B value and got 0.667 meter power of 4. That's all for me.
Hello.
Thank you.
And good morning. My name is Muhammad Manine bin Kamaluddin, KIB1003. So I will tell you about forces in equilibrium in our experiment, which is DOR. So first of all, what is forces in equilibrium? So forces in equilibrium is achieved when Fx and Fy is equal to 0. So which means there is no net force and the force is balanced on the object. So the object is not moving. Alright, so we go to our experiment, which is the door. It's given that F1 is 200 Newton, 1 meter, and the R is 1 meter, and the R1 is 0.2 meter. So we have to search for the F, and we do the Fy is equal to 0 and Fx is equal to 0. So first we do Fy, F minus F1 is equal to 0, F is equal to F1, and then F we get 200 Newton. And Fx is equal to 0, we have no x component, so we did not do the Fx. Alright, that's all. Thank you.
Assalamualaikum. My name is Amir Amzar Fuad. So today I'm going to present the calculation for our moment presentation for LO employ moment and inertia based analysis for problem solving, and use equilibrium based analysis for various structure. So you can see in the picture, F1 is a force going downwards and F is a force going upwards. So the door is at equilibrium. This can be shown that spring F1 has 200 Newton and R1 0.2 meter. So the total moment is 0 because the door is at equilibrium. You can calculate it by equating the moment at spring and the moment at the end of the door equals to 0. Negative 200 Newton because the force is going downwards times the distance 0.2 meter plus with F that we are trying to see, and we get 40 Newton. So the door is at equilibrium.